In this section, we're going to talk about conditional probability. And most of the problems earlier, we actually were doing unconditional probability problems. Like we had a sample space such as the possible rows of a pair of dice, and we would ask, what is the probability of rolling a sum of 7? And to solve this, we knew the sample space had 36 elements. Only 6 of those yielded a sum of 7, so our probability was 6 out of 36. But in the conditional case, what if we imposed a restriction on the sample space but still asked for the same probability? For example, what is the probability of rolling a sum of 7 given that the sum is less than 11? Well, now we have only 33 elements in the sample space because we removed the 5, 6, the 6, 5, and the 6, 6. So we still have 6 ways to get a sum of 7, but the new probability would be 6 out of 33, which reduces to 2 out of 11. And notice that the probability is now different because I placed a condition on it. Let's call A the event of a sum of 7 and B the event of a sum less than 11. And let's take a look how this works out. So the unconditional probability for the sum of 7 was 1/6. But the probability of a sum of 7 given the sum is less than 11 was the probability of A given event B, which was 2/11. Now actually we have a way to write this that's shorter than putting in the term given. So let me give you the notation. So from this point on, the notation that has A with a vertical line through it, B, will actually mean the probability of A given B. And so it will represent the probability of the first event A given the condition B, or just the probability of A given B. So in the above example, the probability of A with no restrictions was 1/6, but the probability of A given B was 2 out of 11. Let's look at another example here. Let me make this a little bit smaller. See if I can make it fit on here for you. Okay, so maybe make it a little bit bigger. Okay, so let's one more time. Okay, so in this example, what is the probability that a person selected has lung cancer? Well, that's one probability, but we could also say what is the probability the person selected has lung cancer given that the person is a heavy smoker, and by heavy smoker we mean 2 packs a day. Okay, now these are both asking for the same probability, the probability that the person has lung cancer, but in the second example I'm actually restricting the population to only those that are heavy smokers. So let's take a look at this in a Venn diagram. Let's say A represents all those people that have lung cancer. So that would be this yellow set here. And let's say B is the event of being a heavy smoker. So that would be these guys here. Okay, so in both questions we want the probability A, but in the second question we added the condition B. So we want the probability of A given B. Okay, so let's look at the Venn diagram. So if I want the probability of A given B, then what I'm asking for, I'm not asking for all of the smokers. I'm not asking for all of the people that have lung cancer. I'm only asking for those people in here because, see, I restricted it to only these people that smoke 2 packs a day. So when I do A given B, I'm only looking at this population in here, and I'm only taking it out of the people that are heavy smokers. So actually, the probability of A given B is simply the number of people that are in A intersect B divided by the number of people that are in B. Okay, So whereas the probability without the condition would be all of the people in A taken out of the entire sample space, but that's not what I'm after. I'm after the probability that they have lung cancer given they're heavy smokers. So I have this group and I take that group out of the heavy smoker group. So the probability would likely change. Now another way to write this, if I divided the top of this by the number in the sample space, that would just change this to a probability. So if I divide the top by the number in the sample space, that becomes the probability of A intersect B. And if I divide the top by the number in the sample space, I'd have to divide the bottom by the number in the sample space, and that would convert that to the probability of B. So this gives me a formula here that the probability of A given B is actually the probability of A intersect B divided by the probability of B. And actually you can solve this formula for the probability of A intersect B by eliminating the denominator here. Just multiply both sides of this by the probability of B, and you'll get that the probability of A intersect B is the probability of B times the probability of A given B. And also, since the intersection is commutative, that is A intersect B and B intersect A are the same thing, you can also say the probability of A intersect B is the probability of A times the probability of B given A. So notice that either one of these is a true statement, and later I'll show you how we can pick which one of these that we want to use based on what we have. Alright, so let's return to our dice problem. Find the probability of a sum of 7 given the sum is less than 11. Well, let's say A is the event of a sum of 7 and B is the event of a sum less than 11. We want the probability of A given B. Well, the probability of A given B is the probability of A intersect B. Well, A intersect B would be all of those that are a sum of 7 that are less than 11. Well, the probability of A intersect B, that's all the numbers that are sum of 7 that are less than 11. Well, that's all 6 of these guys. So all 6 of these fall in both categories. So the probability of A intersect B would be 6 out of 36, or 1/6. So I'll put that on top. And now the probability of B would be the probability of getting a sum less than 11. Well, there's too many to list, but we know there's 33 that are less than 11. So the probability of B would be 33 out of 36, which is 11 out of 12. So I'll put that on the bottom. And now if you take 1/6 divided by 11/12, you get 1/6 times 12 over 11, which actually can be reduced to 2/11. Now, I realize we didn't need the formula before, but these formulas are actually important. And so let me finish this with this last empirical example here. Suppose a survey of 1,000 drivers in a metropolitan area during a 3-year period was taken, and the following results were found. So, here's a table, and so we will answer some conditional probabilities. Suppose we randomly select a driver from this group. What's the probability that the driver is in the 26 to 39 age group given that they have more than 3 accidents? Okay, so let's let A be the 26 to 39 age group, and let's let B be the event of more than 3 accidents. So we want the probability of A given B. Well, that would be the probability of A intersect B over the probability of B. Well, A intersect B would be where the 26 to 39 age group intersects with what was B, more than 3 accidents. So that would be this 25. So this would be 25 out of 1,000. So the probability A intersect B would be 25 out of 1,000. Now let's find the probability of B. All of those that have more than 3 accidents. Well, that's going to be 100. So the probability of B would be 100 out of 1,000. And then if you simplify this, the thousands cancel and you get 25 out of 100 is 0.25. Now, what about the next question? That they had 2 to 3 accidents given they are in the 18 to 25 group. Okay, so let's let C be the event they have 2 to 3 accidents, and let's let D be the event they're in the 18 to 25 group. So now we want the probability of C given D. Well, let's find C intersect D. or the probability of that. So 2 to 3 accidents and 18 to 25. Okay, so here's 18 to 25, and 2 to 3 accidents is 150. So the probability of C intersect D is 150 out of 1,000. And now let's find the probability D. 18 to 25 group, there's 300 of those, so the probability of being in that group would be 300 out of 1,000. So 150 over 1,000 divided by 300 over 1,000 is 150 over 300, or 0.5. All right, next let's do 0 to 1 accidents, given they are in the 40 to 55 group. Okay, so we'll let E be 0 to 1 accidents and F be the 40 to 55 group. So we want now the probability of E given F. Well, we need to find E intersect F. 0 to 1 accidents in the 40 to 55 group, that's 250 out of 1,000. So that's the probability of E intersect F. And the probability of F, we've got 400 in the 40 to 55 group, so that's 400 out of 1,000. And if you simplify this, you get 250 out of 400 is 0.625. Now, notice I can turn this around and find the probability of F given E. And since the probability E intersect F and the probability F intersect E are the same thing, I'm still going to get 250 out of 1,000 for the top. But on the bottom, I need the probability of E, so that would be the probability of 0 to 1 accident. And that would be 575 out of 1,000. So in that case, that would be 250 over 575, which is 0.435. Now, we could have got these without the formula, but I wanted you to see the formula. So for example, to get A given B, just say how many are in A intersect B, and then how many are in B, and so that would be 25 over 100. So that's how I got to 0.25. And to get E given F, how many are in E intersect F? 250. How many are in F? 400. So it's just 250 over 400, and so forth. So let's let that be the completion of the introduction to conditional probability, and I'll work some more examples on the next video.